All right. Let us return to our problem we were looking at last time, where I drew out this circuit. Hold on one moment. Let's keep the noise level down a bit. So I drew this circuit, and the challenge was to find this current I0 flowing through D1 and this voltage V0, which is the node voltage at that node. And as with all these types of circuits, when you're given them, what you're not given is what's the state of the diodes in the circuit. And here's where we're going to use what we talked about last time. The technique of making an assumption and then checking to see if that assumption is valid. We have to make an assumption and we have to check that assumption. So in this case, there are 4 possible combinations, whether D1 and D2 are off. And these are the boundary conditions that we need to check. If a diode is on, VD is going to be equal to 0, and we'll have a positive drain current, or a positive diode current. Excuse me. If the diode is off, then VD is going to be less than or equal to 0, but the current will be equal to 0. And that's what we need to check for the circuit. So let's go and let's make an assumption. I could start anywhere, but I'm going to start by assuming both the diodes are off. And now let's go and let's solve this circuit. So if the diodes are off, then I2 is the current that flows through this diode, so therefore I2 must be equal to 0. I0 must be equal to 0 if both those diodes are off. Now I'm going to give a name to this node voltage here. I'm going to call this VB at that node. So if these two currents are equal to 0, that means I1 must be equal to 0. Because I1 is equal to I2 plus I0 by KCL. And it too must be equal to 0. Yeah?
Is the I2 pointing down like the current through the second diode or through the resistor?
It's going through the resistor and the diode. By KCL, it has to be going through both. This is just a wire. There's no current flowing through the wire.
Oh, does it not connect off with the ground? Oh.
It's going through here and then through here. Same current. There's no current through the wire. That wire I just pull out to show the VO node. There's nothing connected to that.
No.
All right? So those are the same currents, and that current must be equal to 0. Okay, so now let's do some calculations. If that's the case, well, V0 is the voltage at that node. What's V0 equal to? Well, if I2 is equal to 0, what's the voltage drop across that 10K resistor? 0. So if I got 10 volts at this node, what's the voltage of that node? 10 volts. So V0 must be equal to 10 volts. In addition, let's consider VB. I1 is equal to 0. So if VB is, or pardon me, if I1 is equal to 0, again, the voltage drop across that 5K resistor is equal to 0. And in this case, VB must be equal to minus 10 volts. Everybody see this? Because all those currents are equal to 0. This must be true. Okay? So here are our voltages. We've calculated our voltages. We have our currents. So what does this tell us? Well, if both of these diodes are off, then the voltage across each of those diodes had better be a negative voltage. So in this case, what we have is that VD1 is equal to 0 minus negative 10. Or simply equal to plus 10 volts. So 0 minus negative 10 is 0 plus 10. It's equal to 10 volts. VD2 is equal to 10 volts minus negative 10 plus 10 is equal to 20 volts. So for both of those diodes, VD is greater than 0. Are those diodes off? No, they can't be. If they're off, VD has to be negative. They're positive. This isn't possible. So clearly, my assumption is incorrect. I did my calculations. I checked my boundary conditions. Okay, so both of these diodes violated the boundary conditions when I checked them, assuming they were both off. So I've eliminated one possibility. Now, given this elimination, what do you guys think would be the most logical next assumption to check, given what I have here? What?
Both D1 and D2 are on.
Yes, that's excellent. Yes, since they're both violated the boundary conditions, let's try that next. That is the most intelligent choice to make. Let's go ahead and let's assume they are the opposite condition. So in this case, therefore, we now assume D1 and D2 are on. So let's check that assumption. So in this case, if they're both on, that means I must have 0 volts across both diodes. They're basically like a wire. So in this case, what we have is VB must be equal to 0 volts. Because it's simply connected to 0 volts through that diode, which has 0 volts across it. And in addition, V0, okay, if I've got 0 volts here and I've got 0 volts here, what's V0? 0. So 0, 0, 0, because both those diodes have 0 volts across them. Now let's go and let's calculate the currents. So in this case, I2 is equal to 10 minus 0 divided by 10K. And that's equal to 1 milliamp. I1, pardon me. Let's calculate that one. I1 will be equal to 0 minus negative 10 divided by 5K. And that'll be equal to 2 milliamps. So I can calculate those two currents directly. And so now that I know those two currents, then I can calculate I0. So in this case, since I0 plus I2 are equal to I1, I0 is going to be equal to I1 minus I2 by KCL, which is equal to 1 milliamp. All right, so everybody see what I just did here. After this, once I determine I have 0 volts across both those diodes and they're on, everything else is just KCL and nodal analysis. That's all it is. Okay, here are my new results. Now, what do I have? Okay, I2 is the same thing as ID2. It's the same thing as the current flowing through D2. Is that a positive current? Yes, absolutely. What about I0? What's that equal to? 1 milliamp, a positive current. Are both these diodes on? Yes, and the boundary conditions check. So in this case, because of the values of I0 and I2, I know that both of these diodes must be turned on. Now, do I need to check the other two conditions? On, off, and off, on. Is there any need to do that? No. Once you find the right answer, you're done. A diode cannot be both on and off at the same time. So once you come across that next correct guess or assumption and check it, and everything works, you don't violate the boundary conditions, then you stop. So in this case, my answer is therefore that V0 is equal to 0 volts and I0 is equal to 1 milliamp. And that's the answer to my problem. This is how you're going to be working problems for the rest of this semester. Not just for diodes, but also for transistors. Because, as you're going to see, these elements have different operating conditions. And what you need to do is you need to be able to make an assumption and be able to check that assumption. And what you're going to be doing is looking at the boundary conditions to determine the operating condition for that circuit, or for that element. Okay? So questions about this? All right, now let's do something here. I'm going to redraw that circuit. Except I'm making a change to this circuit. I'm redrawing the circuit, and in this case, I am swapping the two resistors. So the 10K and the 5K are now swapped in their position in the circuit. And once again, I want to calculate what I just did here. Okay, so you basically are a person who's very good at memorizing, and you don't want to go to the effort of doing analysis. But you remember this circuit. Professor Holman showed it to you. When Professor Holman showed us this circuit, both those diodes are on. Ah, there you go. I'll write down they're both on and I'm done. But are they? Are those diodes now on? Let us now rework this problem. So in this case, let's assume they're both on. And in this case, once again, if they're both on, then the voltage across this diode is 0 volts. The voltage across this diode is 0 volts, just as we did before. And now, what I get is that I1, first of all, VB is equal to 0 volts. Because I got 0 volts, 0, I've got 0 there, so I know that. And therefore, I also know that I1 is equal to 0 minus negative 10 divided by 10K is equal to 1 milliamp. Everybody see that? All right, so given this, I also know that V0 is equal to 0 volts. Because if I've got 0 volts here, I have 0 volts there. Once again, those two diodes are like short circuits. And in this case, I2 is equal to 10 minus 0 divided by 5K is equal to 2 milliamps. So what is I0 equal to? Well, just as we saw before. Therefore, I0 is equal to I1 minus I2, just applying KCL. And in this case, it's going to be equal to 1 minus 2 is equal to minus 1 milliamps. Okay, let's check our boundary conditions. If they're both on for D1, I0, Okay, so in this case, I0, pardon me, is equal to minus 1 milliamp. Is D1 on? Nope, not possible. Can't be on. Is D2 on? Well, I2 is 2 milliamps, and I've got 0 volts across it. Is D2 okay? Is that violating its boundary conditions? No, that one's okay. So D2 seems to be all right. So what is my next logical guess? Since I know they can't both be on, what would be the next guess you would make, given what I've just seen from these assumptions? Well, D1 can't be on, D2 is on, so what do I guess next? How about we assume D1 is off and D2 is on, all right? So usually your next best guess is to look at any element where the boundary conditions were violated and then flip its operating condition. So therefore we assume D1 is off and D2 is on. 99% of the time, simply flipping the state of the elements where the boundary condition was violated will lead you to the next correct step. So let's do that now. So in this case, we're going to assume D1's off, D2 is on. So in this case, if D1 is off, then I know I0 must be equal to 0. So by inspection, I know that must be true if D1's off. D2 is off. I've still got 0 volts across it, and therefore VO is still equal to VB. We also know that since this current is 0, then I2 and I1 must be the same current by KCL. Okay, so now what do we do? Well, if we know I've got 0 volts here, I can write a little equation for these devices here. This current's equal to that current, so therefore 10 minus V0 over 5K, which is that current, must be equal to VB minus negative 10 divided by 10K. Nothing but nodal analysis. Which is also the same thing as saying V0 minus negative 10 divided by 10K, since VO and VB are the same voltage. So I've got this is equal to that. I can now solve for V0. V0 will be equal to 3.333 volts. And that's my result. Okay. So in this case, what do I have here? Okay. So I know D2 is on. So in this case, I know that I1 is equal to I2, which is equal to 10 minus 3.33 volts divided by 5K. So 6.67 volts divided by 5K. Is that current greater than 0? Yeah. Okay. Clearly, that's a positive current. This is a positive current. 3.33 volts plus 10 divided by 10K must also be positive. And so we see that I2 and I1 are greater than 0. What about the voltage across D1? VD1. What's VD1 equal to? Yes, exactly. VD1 is equal to 0 minus VB is equal to minus 3.333 volts. So the current is equal to 0 and VD is negative. Is D1 on? Is it off? It's off, yes. So it is off. We assumed that D1 is off. Check. D2. I2 is greater than 0. We already checked this. So that must be true. And therefore, V0 is equal to 3.333 volts, and I0 is equal to 0. And there's our result. Do I need to go any further? No. Once I have a solution where the state of the diode matches the boundary conditions, I'm done. Now, why did I work this problem? To show you that if you think that memorization is going to get you through this class, you're in trouble. Memorization isn't going to help you one bit. I took exactly the same problem and changed a couple of component values and had a different result as far as the state of the diodes. Question?
I think I just missed it. How are you able to say that VO is equal to VB?
VO is equal to VB because I've got 0 volts across that diode if it's turned on. So therefore, nodally, they must be the same voltage, which is the same assumption I had up there too. So the D2 did not change. But D1 is off, and therefore I0 has got to be equal to 0. So this is why I say to you guys, even I cannot look at a circuit and just know what the states of the elements are. Because all you have to do is play around with the values in the circuit, and a topologically identical circuit gives you completely different values. So this is what you need to watch out for. Memorization is useless. I'm going to give you the equation sheets. I'm going to give you the diagrams from the book. It's all going to be sitting here in an equation sheet you're going to have in every exam. In fact, it's already on Brightspace. Look at that. Be able to use that material, but you have to be able to write the equations and do the analysis. In a class like this, it is trivial for me to create a circuit you have never seen before. It's not in the book and not in the homework. I can do it in an instant, which means that if you don't understand the analysis technique, you're in trouble. But if you do understand how to do the analysis and how to check your boundary conditions, it is impossible for me to fool you. It's impossible for me to give you a problem you cannot solve. That is the goal of what we're trying to do in this class, to learn how to look at these and critically analyze them using the circuit analysis techniques you guys already know how to use. That's what we're trying to do. Memorization is a complete waste of time for you at this point. If memorization could get engineers through their careers, then we could hire people out of high school to do it and just hand them a reference book. But it doesn't work that way. You've got to be able to think critically. Okay? So, questions? Yeah?
So, right there, like we changed the assumption for D1 and then the original assumption for D2 is still correct?
Yes, so we kept that one.
Is there a scenario where by changing the assumption for one, no longer be correct?
It is possible to create a problem where that could be true, where you might have to go and take a third step and they might actually flip. But I will tell you that from my experience, 99.99% of the problems, once you flip the state of the ones that were incorrect, that almost always is the correct solution next time around. But yes, it is possible to create a problem where that will happen. But in general, you'll see that it won't. The next best guess is the one where you flip the incorrect devices. Other questions? Yes?
When I was doing the board, I did it earlier, and then I used I checked all four assumptions possible.
Well, there's no need to check all four assumptions because once again, once you have a correct assumption and you check the assumption, there's no need to look at the others. So I started with one of the diodes was incorrect, so I flipped that state of that diode and then I reworked the problem. And after that, there's no point in checking the others because the diodes cannot be both off or on at the same time. Just doesn't work that way. Once you have a valid state, that is the valid state. So this isn't like quantum mechanics where Schrodinger's cat, and the cat is both alive and dead. Okay, a circuit cannot be both on and off. A diode cannot be both on and off. It's one or the other. Yeah?
Can't you have indeterminate states with transistors?
You certainly can have indeterminate states in basically unstable circuits, for example.
Right.
That's beyond the scope of this course. This is a linear circuit analysis course, but if you want to take more advanced courses in analog circuit design, where you look at things, for example, like oscillators or memory cells or things like that, then you can have bistable states. But even then, if you solve for one state, then you can get a complete solution. Granted, there are two possible solutions to it, but the point is as a circuit designer, you build this thing so you can flip that state in order, for example, to store a bit in a memory cell.
Right.
Yeah, so that's very possible, but we're not going to be dealing with that in this class. Yeah.
But doesn't that property, that property is unique to logic circuits?
Well, it's not unique to logic circuits. It's also, for example, you can see it in comparator circuits, for example. You can have positive feedback in a comparator, and you can actually have a bistable state. If you took circuits 2, you built a bistable multivibrator that basically flipped back and forth and created a square wave. Remember that? So that was a circuit that was literally flipping its own state back and forth using positive feedback. So it's definitely possible to do that, but we're not going to be normally covering this. That's, once again, kind of beyond the scope of this course. I mean, realistically, I could spend 2 years teaching you guys about electronics. This is a one-semester course. So all I can do here is kind of lay the groundwork and teach you guys the most important part, which is to understand how to apply the analysis techniques. Because once you know that, you can do the rest yourself. And the other classes you take kind of fall into place. I will say that one course I very much recommend to everybody. If you like this course, you like Electronics 1, consider taking Electronics 2 from Dr. Massengill, the follow-on course to this, because he will go into more of this kind of stuff that's beyond the scope of this class. So just, a little bit of sales for one of my colleagues here as far as his class goes. Okay, other questions? All right, in that case, you guys should have everything you need in order to complete the homework problems and turn in the assignment on Thursday. So once again, take a look at the problems. Hope you got those all finished up. I certainly hope you've got LT Spice loaded. You learned how to use that. I did put out an email where I sent out the office hours, so I'm going to be doing those office hours for the rest of the semester. Please feel free to reach out to me if you have any questions. All right? Okay, so let's now move on to a new topic. Let's move away from the ideal diode. The ideal diode is a good way to just learn the fundamentals, but it's not realistic. There's no such thing as an ideal diode. If you could build one, you would be able to violate the second law of thermodynamics. So they're not realistic, but they are a good training tool. What we're going to do instead is we're going to now start looking at how real diodes work. All right, now once again, we're going to keep focusing on this diagram. With VD and ID for the diode. But now we're going to start looking at the actual terminal characteristics of a true p-n junction diode. How does a real diode operate? Well, now if this were a semiconductor physics class, we would spend a couple of weeks going over the equations to derive what I'm going to write for you right now. Once again, if you are interested in semiconductor physics, we have some great classes taught by great instructors, but this is a circuits class. So we're just going to jump ahead and say all the physics people have already done the work for us, and they've handed us this equation. So we're going to start using it. So let's look at VD versus ID. And if we were looking at a PN diode, I'm going to sketch out what the actual characteristics look like, voltage versus current. Now, in some ways, I'm deliberately exaggerating some of the proportions to make things easier to read on this diagram. If VD is positive, this is our region of forward bias. For VD negative, here's our region of reverse bias. So this half versus that half of the diagram. So in this region here, from here to here, and for now we're just going to ignore this. But in this region here, there's an equation that describes the operation of the diode. This is valid for either forward or reverse bias. This region here is the breakdown region. We'll talk about that in just a minute. So this excludes breakdown. Here's our equation. And once again, in a semiconductor physics class, you'd go through some time and effort actually deriving these from first principles. But we're not going to do that. I'm just handing you the equation. All right, let's look at this, and let's see what these terms mean. ID and VD are self-explanatory. They're the voltage and the current for the diode. Once again, defined in this direction. Okay? IS, this IS term is called the saturation or scale current. I sub s is typically a small number. Typically going to be on the order of 1 to 10 femtoamperes for a low power diode. And what's a femtoampere? 10 to the minus 15. It's small. So that's a very small current. So for example, if you've got a diode that's constructed on a semiconductor for an integrated circuit process, that might be a very typical value for the saturation or scale current. Now I sub s, in this case, is proportional to the p-n junction area. Remember how the p and the n junctions merged together and created that depletion region? Well, it's proportional to that. How much saturation current is how large that area is of that junction. It also increases with temperature. So as temperature increases, the saturation current also increases. It's proportional to temperature. Vt is called our thermal voltage. And the equation for that thermal voltage is it's equal to kT over Q. And those are actually parameters you've seen before from your physics courses. K is Boltzmann's constant. T is absolute temperature in degrees Kelvin, degrees Kelvin. And Q is the charge on the electron. Now, of these, Boltzmann's constant and electron charge are never going to change. But absolute temperature, okay, degrees Kelvin, obviously is a function of the environment that the diode is operating in. So, if you plug in the numbers, what you get is thermal voltage is equal to 25.2 millivolts at a temperature of 20 degrees centigrade. Finally, N is called the slope factor. The slope factor is a function of the geometry and the doping of the p-n junction, which is kind of beyond, once again, the scope of the course. But what you'll find is typically slope factor is going to be given to you for a particular diode. In general, values of between 1 and 2 are very typical for the slope factor. For most of the diodes you'll normally see on standard integrated circuits, N is usually approximately equal to 1. And that's normally the number we're going to be using in this class. So we're going to assume, unless I tell you otherwise, a slope factor of 1. It's a good approximation, and it'll be fine for the homework problems we're going to do. In an actual IC process, it might be slightly larger. Once again, that's numbers that the semiconductor characterization people will be able to tell you. Now, the thermal voltage is, once again, a function of the operating temperature. And different books choose different operating temperatures as far as what they consider to be standard temperature. So some books will try to do the temperature more around 27 or 30 degrees C. And they will calculate a slightly higher value for the thermal voltage. But our textbook chooses to use T is equal to 20 degrees. But depending upon the book you look at, sometimes you see 26 millivolts for the thermal voltage. But our book is going to assume 25 millivolts for the thermal voltage. So unless I tell you differently, These are the numbers we're going to use. And once again, I want to warn you, many other textbooks will have VT equal 26 millivolts because they're assuming a higher ambient temperature. For some reason, the authors of our book decided to be a little contrary and do this at 20 degrees C. So their number is a little bit lower. But regardless, we're going to go ahead and just stick with the convention in the book. All right? Questions? All right, now, if we look at this, let's consider what this equation tells us. We notice this is an exponential term, e to Vd over nVt, all minus 1. So let's make a couple of assumptions. Let's consider what happens when we're in forward bias. We're on this side of the graph. So as Vd becomes positive, as Vd becomes positive, we note that e to the Vd over nVt, that very quickly becomes a large number. So very quickly we find that that exponential term becomes much, much bigger than that minus 1 term, which means we can rewrite this. I just dropped that 1, so this is approximately equal to this. So I'm rewriting it now. And once I've rewritten it this way, I can take the natural log of both sides of the equation and I can rewrite it in terms of the voltage across the diode. So it's an approximation, but it's a really good one because very, very quickly that exponential term becomes much greater than 1. Only takes a few tens of millivolts, and it's much, much bigger. So what do we have? Our conclusion from this is that diode current increases exponentially with the voltage across the diode. So we see an exponential relationship between diode current and diode voltage. Vd, on the other hand, increases with the log of the current that is flowing through the diode. So it's a simple exponential equation, rewritten in this case in log form for the voltage. So given this, we can now play a few mathematical games with this equation. Let's assume we have the same diode and we're operating it at 2 different currents flowing through the diode. So let's assume that I'm going to operate this diode at current I1 and I2, two possible currents I can operate it at, and one current's 10 times bigger than the other. So I can either put one current through, I1, or I can put through another current that's 10 times bigger than I1. The question is, what happens to the voltage across the diode, given the fact I have these two different currents that are an order of magnitude apart? Well, let's do it this way. VD1 will be equal to N times Vt times the natural log of ID1, or I should say I1 over Is. Vd2 will be equal to N times Vt times the natural log of 10 times I1 over Is. So two different diode currents two different diode voltages depending upon the currents flowing through it. And one is 10 times bigger than the other. So given this, I'm going to rewrite this. I'm going to say that, let's define delta Vd, which is equal to Vd2 minus Vd1. What's the difference between those two voltages? Well, in that case, this is equal to N times Vt. If I group terms, I'll have one log minus another log. And if you guys remember how to do with logs mathematically, if one log is subtracted, then you can go through and you can take one constant within that log term and divide it by the other. So I can rewrite this and say that this is equal to the natural log of 10I1 divided by Is divided by I1 divided by Is. And if I go through and rewrite these, this will be equal to N times Vt times the natural log of 10I1 over I1 times Is over Is. And in this case, the Is terms cancel, and the I1 terms cancel. And what we wind up with then is delta Vd is equal to N times Vt times the natural log of 10. I'm going to assume N is equal to 1 and Vt is equal to 25 millivolts. Natural log of 10, this will be equal to 57.6 millivolts. Now notice something interesting about this result. I did not tell you guys what I1 was equal to. I just assumed that the current was 10 times larger for I2 than I1. And in fact, what this tells you is if you put two currents through a PN diode, regardless of their magnitudes, as long as one is 10 times larger than the other, the difference in the voltage is going to be 57.6 millivolts, regardless of the starting current. So what you find is delta Vd is equal to, more accurately, is equal to 57.6 millivolts per decade of current. So no matter where I am, what current I'm pushing through that diode, no matter what current flows through it, if I increase that current by a factor of 10, then Vd will increase by 57.6 millivolts. All right? Now, what you'll find is, and let's go back and look at this diagram here. What you will find is typically the drain current is going to be very small near zero. But once again starts to get big and large very quickly because we're heading up that exponential curve. What you'll typically find is this. For a typical PN diode, what you'll typically find is for a standard PN, and I should actually add here a PN silicon diode to be more accurate. You'll find that the drain current, the diode current tends to be small in this region. I mean, I deliberately exaggerated this to show the exponential curve here, but at low voltages, typically for half a volt or less, the current's still small. That exponential term hasn't gotten very big yet. At some point, you're going to hit kind of the knee of this curve where the diode current starts to become much larger, much faster. So the knee of that voltage versus current curve. We give that a name. So somewhere around here, we're going to kind of hit the knee of this curve, and we call this the cut-in voltage. And normally we will say this is VF. VF is the cut-in voltage, or the way to think about this is when you say you've reached V sub F, the diode is really now truly beginning to turn on. You're starting to have a significant amount of current flowing through the diode. So a significant amount of ID starts to appear. And typically VF will be somewhere in the range of about 0.6 to 0.8 volts for most standard silicon diodes. Yeah?
I have a question about the whole decade system that we just saw with just 57.6. Does it go both ways? So if you divide by 10, would it be 5.76?
Yeah, it would be minus 557.6. That's correct. So if you took a current and then divided by 10, as long as you're still in forward bias, then yes, you're going to see that it reduces. So it goes both ways, decade increase or decrease. All right? So yes, you're correct, both ways. Now back to VF, the cut-in voltage. That is typically going to be between 0.6 to 0.8 volts for a standard silicon PN diode. Most textbooks will use a value generally between 0.6 or 0.65 or 0.7 volts, and they'll say that's approximately the cut-in voltage. Depends on the text. Once again, it's kind of, a function of geometry, but those are typical numbers that match with the thermal voltage and the scale factors and the slope factors. All right? So in this class, in general, we will assume the following. So for most problems, we're going to assume a cut-in voltage of about 0.7. Now, notice, I just want to emphasize, you're heading up an exponential curve. So for example, for a particular diode, you may find that it's about 0.7 volts and a milliamp is flowing through it. And then if you increase it by 57.6 millivolts, now you've got 10 milliamps. Increase it by another, you've got 100 milliamps. Then an amp, then 10 amps, then 100 amps. So literally within just a few hundred millivolts from that cut-in, you have enormous currents that can flow through that diode. Exponential growth. All right. Now, one last thing I wanted to point out. I talked before about the fact that IS had a temperature dependence. The scale factor, pardon me, the saturation current had a temperature dependence. And also, of course, the thermal voltage has a temperature dependence. So if you actually look at those temperature dependencies and calculate their effect on this equation, on this diode equation, you get the following result. For a fixed value of ID, so if I have a diode and I put a specific amount of current and keep that current constant, what I will find is this. The change in the diode voltage with respect to temperature will be approximately minus 2 millivolts per degree C. And that is due to the temperature-dependent terms in the diode equation. Okay, so this kind of covers forward bias. Exponential. Now let's consider reverse bias. If VD is less than 0. So once again, there is our diode equation. ID is equal to IS e to the VD over NVT minus 1. For VD less than 0, in this case, this exponential term becomes very, very, very small, much less than the 1. And therefore, in this case, ID will be equal to IS times minus 1 is equal to minus IS. So the diode current is now minus IS. And you notice, guys, I said before, I wasn't really drawing this to scale. Well, that's absolutely true. Because what do we have here? That is the minus IS current, and that's typically going to be femtoamperes. I'd have to draw this on a log scale in order for you to see it. Otherwise, it just looks like it's hugging the x-axis. It's so small. So here's your minus IS term. So what's going on with this current flowing in reverse bias? Well, we talked about this before. Remember, there are minority carriers in a p-n junction, as well as majority carriers. So minority carriers can flow across a reverse bias junction. But there are very few of those compared to majority carriers, and so the current itself is also correspondingly going to be very small. But it's not 0. Now, IS, as I said before, has a temperature dependence in it. We're not going to go into what makes up IS, and I'm just going to normally give you the numbers. But as I said before, IS is typically in the range of anywhere between 1 femtoampere to 10 femtoamperes. So that's pretty typical. They're small values for a standard p-n junction diode. However, if you actually measure the current in the reverse bias region, you'll typically find that the actual reverse current is a lot bigger than IS. It can be, in fact, orders of magnitude larger. What you'll find is that the actual, what we call reverse current of the diode, is much larger. You can find that that can be typically on the order of a picoamperes to nanoamps. So you'll see that the reverse current is generally not femtoamperes. If you actually measure it, you may find instead it's picoamps, much larger than you would expect. Well, that's because there are other things going on in an actual physical diode that are not accounted for in that equation. This is an equation that is derived from the behavior of an ideal p-n junction, so to speak, okay, without any contaminants or any other factors or places for currents to flow. It turns out that this much larger reverse current is due to what's called leakage current. Which is not accounted for in this p-n diode equation. And once again, if this were a semiconductor physics class or a semiconductor devices class, you would talk quite a bit about this phenomenon of leakage current. Again, beyond the scope of this class. But just wanted to point out it is quite often a bigger current. We also find I sub s typically doubles for about every 5 degrees centigrade in temperature. On the other hand, leakage current doubles for every 10 degrees centigrade. Leakage current also tends to increase somewhat as the voltage across the diode becomes more negative. So leakage current is kind of sort of an unknown factor. We're not going to really spend any time investigating it. But what you'll find is, ideally, if this were just nothing but saturation current, this current would be flat. But in an actual diode, you'll find as you make the as you turn the VD more negative, the magnitude of this will tend to increase, and it tends to slope downward a little bit. But once again, this is still going to be a small current compared to the forward bias currents. This is all, of course, happening in reverse bias. So I'm not normally going to be worrying about leakage current. This is not a factor that you guys are going to see in terms of the equations. Normally, we're just going to assume saturation current when we do these calculations. But in real diodes, you cannot ignore the leakage current. In fact, that can actually dominate the behavior in reverse bias. But just for completeness, I wanted to kind of include that, throw that in. Okay, so we've got forward and reverse bias. Exponential current growth, a very small reverse current. Until we get to this region, the breakdown region. What happens there? Okay, let's consider that. Let me redraw this portion of the curve up here, the reverse bias portion. So once again, as I said before, I'm deliberately exaggerating the size of that curve, or basically the magnitude of that IS. I'd need a log scale to see that. But we're going to have a negative saturation current as VD goes negative. Until finally, we're going to hit a voltage where something interesting begins to happen. And I'm going to call that voltage V sub Z. That's a negative voltage, right? Because VD is negative. And when we hit VZ, I'm going to see this. I'm going to see a very, very rapid increase in current as VD becomes more negative. This is not vertical. It is, however, a very large slope. So in this region, I'm in breakdown. VZ is our reverse breakdown voltage. Now what happens is breakdown begins to kick in once I have a large enough negative bias across that diode. And there are two mechanisms that contribute to the breakdown. The first is avalanche breakdown. And this happens for values of VZ which are greater than 7 volts. And this is basically just due to my minority carriers just crossing through the depletion region and then just breaking covalent bonds and causing the current to start to flow. Then a second mechanism is called Zener breakdown. And this tends to happen at lower values of VZ, before like 5 volts, below 5 volts. And Zener breakdown simply happens because the electric field becomes large enough across the depletion region to cause the bonds to break apart and for current to start flowing. So it basically ionizes and breaks those covalent bonds. So this is due to minority carriers colliding with the atoms and breaking the bonds. This is just due to the electric field breaking the bonds. So we're not going to spend any time talking about those mechanisms. Obviously, we would talk about them a great deal. But the result is that once you're in breakdown, what you find is you have a very, very large reverse current in breakdown. But here's the interesting part. It's not destructive. Breakdown is not destructive unless you do something. It's not destructive unless VZ, the magnitude of VZ times ID, exceeds the power rating for the diode. So as long as you don't allow the diode to dissipate too much power, you can bring the diode back out of reverse breakdown and it goes back to normal operation. But if you push too much current through the diode and the diode gets too hot, literally the p-n junction begins to melt. And at that point, the diode is destroyed. But it turns out there's something very interesting about breakdown. We can make that VZ value very predictable. We can actually engineer a diode so that the diode always breaks down at a certain value that we can predict. And in fact, this leads to a whole interesting type of component we'll talk about later called the Zener diode, which is very useful for voltage regulation because it lets us set a particular value based on that breakdown value. And we're going to be doing problems with that later on. So we're going to come back to this. But for now, we're going to go ahead and we are now going to move on and then start looking at how we can do analysis in forward bias using the diode equation. Yeah?
Is the voltage-current relationship in breakdown linear? Or is it
Basically, in this region here, it's essentially linear. And once again, when we actually talk about that later on, we'll look at that. So this is not perfectly straight, but it's going to be very steep. But we actually do treat it as a linear element, which mathematically turns out to be very convenient. We'll see that later. Okay, so we're going to leave this behind now. We've looked at the three regions, forward, reverse, and breakdown. Next time we'll start looking at how to do calculations in forward bias, which is where we're going to really care. Most of the calculations are going to be when we care about that diodes are turned on. All right, we'll look at that next time.